At this very moment, you are falling through a hole in space 2 billion light-years wide. This is not science fiction. This is our cosmic reality, confirmed by astronomers in 2013 and largely unknown to the world at large. We inhabit the KBC void, a vast cosmic desert where matter exists at densities 20% lower than the universe's average. This emptiness is warping our measurements of reality itself, making the universe appear to expand faster here than anywhere else and breaking our most fundamental equations of cosmology. 3 astronomers were counting galaxies when they noticed something impossible. Ryan Keenan, Amy Barger, and Lennox Cowie examined 35,000 galaxies, mapping their positions across billions of light years. The numbers refused to align with predictions. Everywhere they looked near Earth, there were fewer galaxies than there should be. Not slightly fewer, 20% fewer. The pattern stretched outward in every direction for 1 billion light years, forming a sphere of cosmic emptiness with us near the center. This was not a small gap between galaxy clusters. This was a void on a scale that should not exist according to standard cosmology. The researchers triple-checked their data, used multiple galaxy surveys, and examined the sky from different angles. The result remained consistent. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs everything else we have ever observed. The discovery earned a name that sounds almost casual, the KBC void, using the initials of its 3 discoverers. But there is nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them. That is expected. But a region this enormous with such a significant deficit of matter pushes the boundaries of what random chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do, it requires exceptionally rare initial conditions. The statistical probability is less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density, meaning it is so unlikely that you might not find one in the entire observable universe. Yet, here we are, living inside one. The implications began cascading immediately. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates, depending on whether they look at the ancient universe or the nearby universe. The numbers disagree by 9%, which sounds small but represents a crisis. Both measurements are incredibly precise. Both should give the same answer. They do not. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it, adding extra velocity to their motion away from us, and making the local expansion appear faster than average. Suddenly, the conflicting measurements made sense. We are not measuring the universe incorrectly. We are measuring it from inside a hole. Cosmic voids are not truly empty, which makes them even stranger than their name suggests. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. Scientists confirmed this through careful observation. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls from the mountains toward the valley, but since we are talking about space rather than terrain, that pull makes galaxies fall outward, not inward. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. Only when scientists began measuring galaxy redshift systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody expected. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness, punctuated by occasional concentrations of matter. The Milky Way is not at the center of the KBC void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. The void extends outward for 1 billion light-years in every direction from its center, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard. Yet even this supercluster resides within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. Our galaxy is rushing away from the local void at 600,000 miles per hour, driven by gravitational imbalance. This motion is separate from the overall cosmic expansion. It is a peculiar velocity, meaning it results from local gravitational effects, rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate, because they add extra motion on top of the expansion signal. Every measurement you have ever heard about the universe's expansion rate might be wrong, not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. The second method looks at nearby objects with known brightness, specifically type Ia supernovae and Cepheid variable stars. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise, with very small error margins. Both should give the same answer if cosmology is correct. They do not. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we are measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. The Hubble tension is not just an inconvenient disagreement between two measurements. It represents a fundamental challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, the standard model of cosmology. This model has been spectacularly successful at explaining observations from multiple sources, but the Hubble tension suggests something is missing or wrong in this framework. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement is correct globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is impossible. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000, but they were enough to set the stage for everything that followed. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away toward the collapsing overdense regions, the underdense regions became even emptier. These underdense regions evolved into voids. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. Satellites have mapped these temperature variations in exquisite detail across the entire sky. Scientists can take this pattern and run it forward in computer simulations to predict how structures should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. However, the simulations rarely produce voids as large or as deep as the KBC void. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament, but probability distributions matter. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. When you picture the universe, you probably imagine a sky full of stars and galaxies. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. If you could travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The KBC void defies probability in a way that makes cosmologists deeply uncomfortable. Standard cosmology predicts that structures form through gravitational collapse of initial density fluctuations. The larger and deeper a structure, the rarer it should be. Computer simulations of structure formation using the lambda-cold dark matter model rarely produce anything this extreme. Some studies have estimated the improbability. One analysis calculated that a void of the KBC's size and depth represents a 10 sigma deviation from the expected density. In statistics, a 5 sigma result means there is less than a 1 in a million chance of it being random. A 10 sigma result is incomprehensibly unlikely. Cosmic voids are the best places in the universe to study dark energy, because voids are the only regions where dark energy dominates completely. In dense areas like galaxy clusters, gravity is strong enough to resist cosmic expansion. But in voids, where matter is sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. The voids expand faster than the cosmic average, driven by dark energy's repulsive pressure. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of the universe's total energy. It behaves opposite to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. The exact nature of dark energy remains unknown. Galaxies inside cosmic voids grow up in profound loneliness. Unlike galaxies in dense clusters that interact frequently with neighbors, void galaxies evolve in isolation. Void galaxies tend to be smaller and dimmer than galaxies in filaments. They have lower masses, containing fewer stars and less overall matter. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers are a primary driver of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed. The Laniakea supercluster is a mind-bending structure that redefines what we mean by our cosmic neighborhood. Identified in 2014, Laniakea contains roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven. Here is the paradox. Laniakea, despite containing 100,000 galaxies, resides entirely within the KBC void. The KBC void is primarily defined by the absence of rich superclusters and large galaxy clusters at its center. Within that enormous volume, there is still plenty of matter, just not as much as there should be on average. Baryon acoustic oscillations are frozen sound waves from the early universe, and they have become the most reliable ruler for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were coupled together. Sound waves rippled through this plasma, creating oscillations in density. When the universe cooled enough for atoms to form, the sound waves froze in place. The distance these waves traveled before freezing left an imprint on how matter is distributed today. The cosmic microwave background radiation fills the entire universe with faint light left over from the Big Bang. Its temperature is remarkably uniform at 2.7 Kelvin, just above absolute zero. But that uniformity is not perfect. Tiny temperature variations exist, typically only a few millionths of a degree different from one direction to another. When light enters a void, It experiences less gravitational influence than light passing through dense regions. This creates a measurable effect called the integrated Sachs-Wolf effect. The photon ends up with slightly less energy than it started with, which shows up as a temperature drop. The void's existence has led some scientists to question whether gravity itself needs revision. The standard theory of gravity is Einstein's general relativity, formulated in 1915. It has passed every test thrown at it for over a century. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda cold dark matter, perhaps gravity does not work exactly as Einstein predicted on the largest scales. Modified Newtonian dynamics, or MOND, is the most prominent alternative gravity theory. MOND suggests that gravity behaves differently when accelerations are extremely small. In MOND cosmology, structures form more efficiently because the enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The age of the universe is one of cosmology's most important numbers, and the KBC void puts it in jeopardy. Current measurements based on the cosmic microwave background place the universe's age at 13.8 billion years. But if the local expansion rate is genuinely faster than the cosmic average due to the void, those models could be wrong. If the Hubble constant measured locally represents the universe's true expansion rate rather than a void-distorted local value, then the universe has been expanding faster throughout its history. A faster expansion rate means the universe reached its current size in less time. The oldest stars in our galaxy pose a stubborn challenge to any cosmological model that makes the universe significantly younger. These ancient stars, found primarily in globular clusters and the galactic halo, contain very little metal. The most metal-poor stars we observe today must have formed very early, before much metal enrichment occurred. Their ages tell us directly how long ago the galaxy formed. Globular cluster ages derived this way consistently come out to around 12.5 to 13 billion years. Galaxies are not stationary. They move through space in response to gravity from surrounding structures. These motions are called peculiar velocities because they are peculiar to each galaxy, distinct from the overall cosmic expansion. Observations tell a different story than standard cosmology predicts. Measurements of galaxy velocities using multiple techniques show significant bulk flows extending to distances of 200 to 300 million light-years. These flows reach velocities of 400 kilometers per second or more, far higher than standard cosmology predicts. The KBC void is not the largest underdense region known. That distinction belongs to the Eridanus supervoid, discovered through its impact on the cosmic microwave background. Located in the constellation Eridanus, this void is roughly 1.8 billion light-years across. What makes the Eridanus supervoid particularly intriguing is how it was found. Astronomers did not discover it by counting galaxies. They discovered it by noticing an unusually cold spot in the cosmic microwave background temperature map. The term Hubble bubble has emerged to describe a troubling observational pattern. When astronomers measure the Hubble constant using nearby objects like supernovae within about 2 billion light-years, they get higher values. When they use objects farther than 2 billion light-years or rely on cosmic microwave background data, they get lower values. The boundary at roughly 2 billion light-years is suspiciously close to the edge of the KBC void. Cosmic voids act as filters, preventing certain types of structures from forming within them. In dense regions of the cosmic web, galaxies collide and merge frequently. Small galaxies combine into larger ones. But in voids, this trajectory is blocked. The low density in voids means gravity is weak. The matter density is simply insufficient to pull together such massive concentrations. As a result, voids remain perpetually underdeveloped. Dark energy is accelerating the universe's expansion, and that acceleration has dire implications for the far future. As space expands faster over time, structures that are not gravitationally bound together will drift apart and eventually lose all contact. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The universe's fate is increasing isolation, with structures becoming islands separated by ever-expanding voids. We are inside a cosmic hole 2 billion light-years wide. This is not metaphor or speculation. This is observation. The KBC void is real. Its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, whether it makes us unusually positioned in the universe, these questions remain open. But one thing is certain: the universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. As we continue deeper into the captivating story of the cosmic void, the narrative takes us further into the implications, physics, and mysteries that define our extraordinary position in the universe. The intricate foam-like architecture of space reveals itself not only in the presence of vast emptiness, but in the connection of filaments, superclusters, and galaxy walls. The cosmic web is a testament to gravity's work over cosmic time-building, sculpting, and distributing matter into patterns so grand, they defy ordinary imagination. Our place within the KBC void makes every local measurement about the universe more complex. The peculiar velocities, the biases of our vantage point, and how distance affects the expansion measurements, all combine to present a challenge for understanding cosmic truths. When we look outward, we are seeing not the universal average, but a unique patchwork, and must be careful interpreting what we find. As we probe beyond the edge of our void, cosmologists hope to break past the Hubble bubble and see whether the greater universe operates on principles different from those our local measurements suggest. Even deeper, the KBC void amplifies questions about the cosmological principle, the idea that the universe looks the same in every direction and that no place is special. Yet, living inside one of the largest supervoids ever detected subtly undermines that assumption, pushing cosmologists to revisit the foundations of their models, their simulations, and perhaps reconsider the role of luck, or modification, in cosmic structure. The nature and evolution of voids are closely tied to mysterious cosmic components, dark matter, and dark energy. Dark energy, especially, claims dominion within the void, subtly steering the expansion with repulsive pressure, while gravity's weakness leaves the region in a state of ever-increasing emptiness. Thus, voids become natural laboratories for testing the properties of dark energy and for monitoring the ways the universe itself transitions from one dominant force to another as it ages. Within the boundaries of these vast cosmic hollows, galaxies themselves are transformed by loneliness and isolation. They grow in relative peace, often untouched by the violence of mergers common in filaments or clusters. Their star formation processes and chemical evolution can hint at alternate paths for galactic maturation, while their morphologies and dark matter halos embody the unique fingerprints of the void environment. These galaxies also offer clues to the prospects for life, with stability and isolation serving as a double-edged sword. On one hand, fewer catastrophic events might allow life to develop in peace. On the other, low metallicity and sparse resources could limit such opportunities. The void thus stands as a natural experiment in cosmic habitability and evolution. On grander scales, structures like the Laniakea supercluster showcase the duality of emptiness and structure within the void. Rich in galaxies, yet surrounded by vast underdensity, such superclusters make clear that emptiness does not mean uniformity, and that our cosmic neighborhood brims with paradoxes to unravel. All of these effects ripple outwards, influencing observations of the cosmic microwave background, driving bulk flows, altering the expansion profile, and presenting mounting evidence that gravity, structure formation, or initial conditions might need revision to fully explain what we see. In the distant, accelerating future, the universe's fate will be dominated by ever-expanding voids. Structures will become isolated islands, star formation will cease, and eventually, even light from neighboring galaxies will fade. For civilizations within these cosmic hollows, the story of the universe itself may be forever veiled behind inaccessible horizons, with cosmic clues growing fainter, mysteries deepening as isolation intensifies. Thus, our position within a vast cosmic whole becomes the stage for one of the most profound scientific dramas ever conceived. Every discovery within it shapes not only how we understand our own patch of the universe, but also how we infer the nature of reality itself. The universe, as it stands, is stranger and more wonderful than any simple answers can convey, and our journey through the science of this cosmic void is far from over. We are cosmic castaways, drifting through a desert of space, measuring a universe that may not be what it seems. The mystery is as deep as the void itself, and the questions we ask within its boundaries echo across time and space, beckoning future explorers to unveil new truths about existence itself.